Okay, well, good morning, everybody, and welcome to this webinar where I'm going to be talking about how Zing improves Java performance. And the idea really behind this presentation is to give you more of an idea about what we at Azul do in terms of our Java virtual machine so that we can help to improve the performance of your application without you having to do anything in terms of the code that you're writing. So it's about invisible application performance improvement. My name is Simon Ritter. I work for Azul as our Deputy CTO. I describe that as being the understudy to Gil Tene, who's our CTO and who's been responsible for a lot of the technology that I'm going to talk about in the rest of this presentation. Presentation will be about half an hour in length, and if there are any questions, please feel free to type those in the question box as part of the webinar. What I'm going to do is I'm going to leave questions until the end, and then I'll have a look at questions, and if need be, I can answer those at the end. So I won't be answering questions as we go through. Right, so if we begin. Now, the thing about Java is that it relies on a virtual machine, and that's been one of the big selling points right from the very beginning, is this idea of write once, run anywhere. And what that allows the system to do is to take care of a lot of the details for you. So if you're a Java application programmer, you're familiar with this, you know all about this. And if we look at how Java has developed over the last 20 years, you'll find that back in the very early days, Java, the virtual machine, was a very simplistic approach to solving the problems that it needed to do. And there were really three things that it needed to handle big tasks for application code. One was to take the bytecodes that have been compiled by the compiler, intermediate code, and convert them into the native instructions of the platform that you're running on. Second thing was memory management, so the whole idea of allocating space for objects, reclaiming that space through the garbage collector. And then lastly, the idea of multi-threading and coordinating threads and how they lock things. Now, obviously, over the last 20 years, Sun and then Oracle have done a lot of development work on Java in the virtual machine to improve the way those things work. So now there's adaptive compilation, there's a client compiler, a server compiler, there are a range of different garbage collection algorithms that can be used in terms of concurrent mark sweep, there's the G1 collector, there's the parallel collector, the serial collector, and so on. And that's great because it provides a very good general purpose way of running applications. What we at Azul have done is to develop another Java virtual machine, but it's not really developing a completely different virtual machine. It's the idea of taking Java JDK from the open source project, the OpenJDK, and reusing that so that we can improve the way certain things work. And what we really want to do is to sort of, rather than taking a very broad approach to all possible types of applications, what we've done is said, well, let's focus our JVM on applications which are specific types of applications. So these tend to be things which are low latency applications or applications which require a lot of data in memory, so big enterprise applications. What we wanted to do was to eliminate some of the problems that you get with Java running on top of other Java virtual machines. So we're looking at continuous responsive platform. What we don't want is big pauses where the platform goes off to do things. As I said, one of the key things here is that we base our version of Java on top of the same source code that Oracle, IBM, Red Hat, other licensees all use. So we take the OpenJDK source code and then we replace certain parts of that. So at the moment, the biggest thing that we replace is the garbage collector. We also do other things around improving performance. So we're always looking at ways that we can improve the performance of application code without you having to make any modifications to your actual code. Because we take the standard OpenJDK, we make modifications, it's very important that we verify that we are still completely compliant with the standards so that you can run your code unchanged. We do that by running the TCK, the Test Compatibility Kit. We pass all of those tests. We can guarantee that what we are supplying as a JVM and as Java is exactly the same from the standards perspective as what you would get from any other provider. So the great thing about that is it is a drop-in replacement. You take our JVM, you put it where you have the JVM before, and you can run your application code without any problems. Now, there may be some very minor issues if you're using some of the APIs which are outside of the standard. Some of the sort of non-standard APIs may require some testing, but if you're using standard Java, then it is a drop-in replacement and you can just run your application code unchanged. So in terms of the big things that we do with our JVM, the first is to eliminate problems around garbage collection. The way we like to describe it is that we have solved the problem of garbage collection. What we do is, as I said previously, is to take the garbage collection system and the memory management system out of the JVM, the OpenJDK version, and we replace it with our version. What we call this is the concurrent continuously compacting collector, or C4 for short. Now, the big difference between our collector and the collectors that are used in any other commercial JVM is that we do not have a situation where if the load in terms of memory being placed on the JVM gets so high that the garbage collector can't keep up with allocating space in the old generation for objects, what will happen with other commercial collectors is they must fall back to a full compacting collection. Now, this is a problem because if you fall back to a full compacting collection, you have to pause the application threads. Pausing the application threads means that your application stops running in effect. And the amount of time that it takes to do a full compacting collection on the old generation is proportional to the heap size. The bigger your heap, the longer those pauses are going to be. So if you're lucky, then maybe only a few milliseconds, or if you're running a very big heap, you could be looking at seconds, minutes, even hours potentially. So we don't want to do that. And what we've done is to replace the collector with one that doesn't have the idea of doing a full compacting collection. So it's designed to work in a very wide operating range. As I said, it's really ideal for low latency applications where you need guaranteed responses within a certain period of time. And so we will do that across the full range of running your application rather than having situations where you may get long pauses. Our collector will not do that. We also work with the idea of having very big in-memory applications. So a lot of people will try to avoid long pauses using the full compacting collector by making the heap space small. If you've got a lot of data, you need to multiply the JVMs up, and you've got all sorts of problems with distributed data. What we can do is we can run in very big heaps without these long pauses. So anything from 1 gigabyte all the way up to 2 terabytes. And we can handle very high allocation rates, anything from 10 megabytes all the way up to 20 gigabytes a second of allocating objects. We're actually working on bigger heaps. We have customers who are asking us to provide support for even bigger heaps than 2 terabytes. Other things that we're doing, there's a kind of second area that I want to highlight here, is improving the way that we analyze what is happening with garbage collection, because we need to maintain information about how your application is working in order to figure out how to get the garbage collector to work in the most optimal way. At the moment, what we do is we take a fairly simplistic approach to that, which is to look at the rate of allocation of objects at any particular, and we use that information to predict when we're going to need to run the garbage collector next. So we can use that information and we can set up the garbage collector to run. It runs concurrently, so we can still do work for your application, but it's, as I say, a fairly simplistic approach, which works very well in most applications. But what we've noticed is that there are certain types of applications, certain profiles, where that may not be the most optimal solution. And you'll get situations where you get intermittent spikes in allocation, where suddenly something happens in your application, a lot of data needs to be allocated, and that can cause the way that we predict the garbage collection to be run to change a little bit. And it would be better if we could do some more advanced approaches to gathering that data and figuring out when to run the garbage collector, which is what we're doing now with the improved garbage collection heuristics. What we now do is look at a sort of sequence of how data is being allocated within your application and use that to provide a more detailed prediction rather than taking a single value and then predicting it that way. So this gives us a better way of predicting. We can get the garbage collector to run more quickly if need be. We can let it run for, or let the application code run for longer if need be. It just gives us a better way of predicting when we need to do garbage collection versus what we're doing at the moment. Clearly, we obviously need to make that dynamic, so we don't just keep all the data. We collect data as your application is running. We keep that data for a certain period of time so we can see how your application profile is changing over time. So it's very much a dynamic approach to establishing when the garbage collection needs to run. Another thing that we've done in our latest release is looking at how we can provide support for some of the latest hardware. And again, the reason behind this is use advances in terms of the very low-level hardware to provide improvements in performance for application code. And one of the biggest ones that we've just introduced in our last release is the idea of speculative locking. Now, what this does is it uses restrictive transactional memory, which is now supported in some of the latest Intel processors. So the Haswell and the Skylake processors have this support provided in them. And Intel have added some new instructions to the instruction set. There's TSX extensions, which allow you to make use of this transactional memory. So it's actually the hardware that is enabling support for this feature. And what we can do for the JVM is if we know we're running on one of these processors, we can then take advantage of that. But it's completely invisible to your code. So you still think you're running just the standard Java code, you're doing exactly what you were doing before, but suddenly our JVM is looking at your code and saying, you're doing some interesting things with locking. We can do some things within the JVM to optimize that using the underlying hardware and make things run more efficiently and improve the performance of your application. Now, the way that this works is that if you have something like a hash map, so you've got a collection of data and you want to do continuous updates to that data, you want to read from the data, you want to write to the data. Now, if you use just a normal hash map, that's not synchronized, so you would need to provide some sort of locking around that to ensure that if you're changing data within the hash map, that when you read at the same time as writing, you don't get a problem of inconsistent data. Now, that can be quite a heavy weight operation because with each object in Java having only a single monitor, you can end up with a problem of heavyweight locking and multiple threads all contending for the lock at the same time. And quite often you have a situation where multiple threads are all trying to access the hash map at the same time, but they are looking at separate pieces of data. So there's no contention, there's no problem in terms of how that data can be accessed. So even though you need to have the locking to prevent potential problems, in a lot of cases there would be no problem. So you could, in theory, not have the locking there, but your code obviously needs to have it in there. What we do is we say, right, because we can use the transactional memory support underneath in the hardware, we can allow you to think that you're taking a lock on that particular piece of code and that particular piece of data, but by using the transactional memory underneath, we don't actually have to take the lock. So it's the hardware that provides support for that. And then if we've got the idea of doing puts to multiple different indices within our hash table, then we can do that independently without having the overhead of the lock. If we get a situation where there is conflict of data, two threads do start trying to access the same piece of data, then the transactional memory will kick in, it will throw a trap, and we will then be able to revert to a situation where you do acquire the lock in order to protect that data and have the consistency maintained. But the great thing here is that you don't have to make any change in terms of the way that your code works. And we did some benchmarking on this using gigaspaces as a sample application, and we found that if you looked at the put and the get results, we were getting about a little bit more than twice the throughput that we would get without using transactional memory. Interestingly, if you do things like remove, it does run slightly slower when you use transactional memory, and that's just as an effect of the way things work. So if you've got a situation where you're doing lots of puts, lots of gets, transactional memory is good. If you're doing lots of removes, which could be a rather unusual situation, then you might need to evaluate whether it makes sense to turn this option on or not. So it's there if you want it. A couple of other things that we've done in terms of the support for the latest Xeon architectures. There's some better support for vectorization within these processors. So there's actually double the size. So it's moved from 128 bits to 256 bits for the single instruction multiple data way of doing things. So there's these extensions again, AVX and AVX2, which we're now making use of to improve performance there. And also we've provided an improvement in terms of the way that array copy works for primitives. And there's an option which is on by default, use unaligned load stores, and that will improve the performance of an array copy. So if you're doing a lot of array copies, then another good thing in terms of improving performance. Ready now. One of the things about the Java application is that it uses adaptive compilation. As I said, in the very early days, you simply had the idea of bytecodes being interpreted. So it was a fully interpreted mode. What happens now in our code is that you start off your application and the classes are read, the methods that within those classes start to execute, and they're executed by interpreting the bytecodes into the relevant instructions for the hardware platform you're on. What will happen over time is that adaptive compilation will notice the hotspots, hence the name of the hotspot virtual machine. It will notice the hotspots in your application code. So certain methods will be run more frequently than others. And once it identifies those methods, it will start to compile them into native instructions. That way it doesn't have to do the interpreting every time, and over a period of time your application will get to a state where it's running all of the typical methods that it's going to use, and what you'll see is you get better performance. Now, as I said, there's two different compilers that are used there. There's the C1 compiler, which has a faster startup profile but a lower optimum level of performance, and then you've got the C2 compiler, which gives you a slower warm-up profile but a better overall performance level. And in more recent JVMs, that's actually been combined, so you can switch from C1 to C2 to give you the idea of a quick warm-up, but then warming up slightly longer and giving you better overall performance. Now, the drawback of that is that when you run your application, it runs and everything gets up to speed and you've got a nice fast application. Then you have to restart your application and you're back to the beginning again. So you restart your application, everything resets, then you've got to load the classes, you've got to do the adaptive compilation, you've got to go through the whole process of identifying hot methods, compiling them, and so on. What we really need is a situation where we go through this warm-up, we get to a point where we've got optimum level of performance, and then when we restart the application, what we actually get is full speed of our application. So wouldn't it be nice if we could do that? And that's what the Ready Now feature that we include with the Zing JVM does. So the idea is that you go through the warm-up process, start your application, go through the interpreted mode, get the hot methods, get them compiled into native instructions. And then when you reach a certain point, you decide that you're going to stop your application, and a profile is recorded of what your application looks like. Now, it's important to kind of make the distinction here. What we're not doing is simply taking a snapshot of what the virtual machine has in memory. So we don't take all of the compiled code that you would have at that point in your application, because it's not quite as simple as that. In fact, it's actually a lot more complicated than that. Because of the dynamic nature of Java, you can have dynamic class loading, you can have inheritance, you can have different classes, subclasses, and so on. All of that means that you can't simply take a snapshot and say, right, we're going to restart the application as if it has never stopped. There could be a lot of situations where things in that situation wouldn't be correct. So we need to be very careful about how we do this. We don't simply record a snapshot, we record a profile, which in essence lists which methods are hot, which methods from which classes have been compiled, and associated data with that. What we then do is when we start the application again, we will use that profile to help the JVM to optimize things at startup time. Now, if you look at the way that if you go into the JVM specification, you'll find there's a lot of detail about what actually happens when the JVM starts up, when an application starts up. So, as I said, you can't simply take a snapshot of the code and start running it again. What you need to do is you need to go through the appropriate process of loading the classes, initializing the classes. But because we have this profile, we can immediately say, this is a hot method, let's compile that method, and as the application starts running, we're then able to have the performance of that application very rapidly come up to the full speed that we had before based on the profile that we had. So this is a very useful feature if you're looking to be able to restart an application and get the kind of performance that you had when it was running before without going through that whole warm-up phase. So another thing about this is ways to improve the performance of that. There's a couple of things that we've done. Well, one thing specifically we've done in the last release of our JVM was to reduce the number of what are called de-optimization save points. As methods cool down and you stop using them, the compiler will actually, in effect, throw away the code because it doesn't need it anymore. It will use the space for other methods which are hot at that particular point in time. This is, you can think of it very much like the way that the garbage collector works. And because the garbage collector needs to make sure everything is consistent, same thing with the compiler. So you have what are called safe points to ensure that everything knows exactly where everything else is. And then at that point, you can do the de-optimizations. So we've reduced the number of safe points that we require for that, which again will improve performance. We're also looking at things in the future, how we can make better use of both the C1 and the C2 compilers to, again, optimize code even further, give us a better way of starting up and getting better performance right from the very beginning. A couple of things just to give some examples. I already mentioned the idea of the benchmark earlier on that we were looking at in terms of how we can improve things. This is really a sort of like-for-like comparison. I'm not really trying to show specific numbers here, but one of the things that proves to be very popular with our JVM is the Cassandra database system. And what we've done is we've measured the performance using the standard Cassandra benchmarks. And you can see here on the left we've got the blue bars, which represent the previous version of Zing, and the red bars, which represent the latest version of Zing. As you can see, the three in the middle there, we've got quite a good improvement of performance. The one on the left, a small improvement in performance. E, we've got a little bit of improvement in performance. And F is probably about the same, a very slight degradation in performance, but that's the kind of thing we will look at and go, okay, this is a regression. We will need to identify why we didn't get either the same level of performance or improvement in performance there. And so it'll be something that we'll work on and ensure that that is resolved so that we get at least the same level of performance. Similarly, if we look at a few of the sort of spec JVM benchmarks, this is always useful to see what kind of things are going on, again, to evaluate performance. I just picked out three here. There's a lot of different benchmarks that make up spec JVM. The other ones were all sort of slightly better, but not hugely better, so I just picked out three which gave us significantly better performance. MPEG audio, I'm guessing that most people, if they're doing enterprise applications, that won't be a big feature for them, but yeah, we've got a 10% improvement in performance. And then for two of the scientific benchmarks, both large and small in terms of the LU benchmark, we got really significant improvements in performance here, so 130% and 162% versus the previous version. And that's the sort of thing where if you're doing enterprise applications, you're doing big number crunching type applications, throughput like that will be very noticeable in terms of your application performance. Just a couple of very minor points as well, things that we've added in the last release just to, again, improve performance. Optimization on non-static final fields. There's an option for that which is turned on by default, so you don't need to really worry about that. It will just improve the performance of non-static final fields. And if you want to use encryption, again, what we're doing there is saying, well, there are certain situations where the hardware will support hardware encryption, and we can get better performance from that rather than doing it in software. In this case, it's to enable parallel support. So there's an option if you're using AES encryption and you can turn that on in order to get parallel support for your encryption. Just to kind of wrap up and conclude then, Zing is a great JVM. It's ideally suited to these types of enterprise, low latency applications where you don't want potentially long pauses in terms of garbage collection when you fall back to a full compacting collection. It's also, because of the fact you can scale to 2 terabytes in terms of the heap space without having these long pauses, then big in-memory applications are also very, very suitable for this. And even, if you're looking for throughput, some of the things I've demonstrated, those will work very well in types of applications as well. Always looking for ways to innovate in terms of improving performance. So we've very much been known for a company that's worked on garbage collection. We're looking at lots of areas around that with things like ReadyNow, with things like restricted transactional memory and things like that. So there's a lot of things that we're trying to do here. Certainly, if you're interested in trying this out, you can do that for free. So although it's a commercial JVM, you go to our website, there's a free trial. You can download the JVM, install it, run it on your application, compare the performance against other commercial JVMs, and then if you feel that that's giving you the kind of performance you want, then you can come and talk to us and we can discuss terms of a commercial license. So with that, that's the end of the presentation. I've got a couple of minutes left here, so I'm just going to see if anyone's asked any questions. Let's have a look. Questions, there we go. Okay, right, so I don't see any questions. So maybe somebody is asking a question. Let's just look and see. Okay. Right. Okay, well, I'll give you one example question because I've got like 1 minute, because I know this was a question that somebody asked me just the other week when I did a similar presentation. This was how we can avoid the issue of full compacting collections, which other people don't do with their commercial collectors. And really the way we do that is by having what's called a read barrier rather than a write barrier. So essentially we will allow the application code to continue running and accessing areas of memory, objects in memory, and be able to write to them as we're moving those objects around. And so every time somebody tries to read from an object, what we'll do is we'll check that the reference is still correct, and if it isn't, we'll adjust the reference and then allow that application code to take the reference and use it either to read or write. So that will avoid a lot of the problem. That's not a heavyweight operation, so we don't see a reduction in performance by doing things that way, but it does allow us to avoid these long pauses because we can do things continuously and concurrently with application threads. So I think with that we're pretty much on 10:30, so thank you very much to everyone for listening to this webcast, and that is the end. Thank you.